Hi everyone, I'm John Poprosky and welcome to my webinar on a free IBIS-AMI model generator for a receiver with a CTLE, CDR, and DFE that can be used in any channel simulator. Please type any questions into the chat as I proceed with this webinar. I'll have a questions and answers session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? High-speed digital SerDes design integrated circuits have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or to own. Today, the SerDes channel simulation technology has matured so that it is available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations or from hardware measurements. This webinar is to let you know about the process I have used for many years to generate IBIS-AMI models from any channel simulator, and it's available to you for free. I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40 plus high-speed digital integrated circuit companies over the past 10 plus years. Over that time, I learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI model building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools, Microsoft Visual Studio, CMake, web browsers, HTML, and more. I learned that creating an IBIS-AMI model should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct circuit simulation or measurement data and use automation. My tools rely on automation to generate models from measured and simulated circuit data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows or Linux machine. I am here to share my learnings over the past 10 plus years and introduce you to the same IBIS-AMI model generation capability I have used to create and deliver high quality, low cost IBIS-AMI models. What this webinar will show you. This webinar first gives an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to create IBIS-AMI models for a receiver with a CTLE, a CDR, and a DFE. Define the CTLE with circuit waveforms. Define the CDR with its observed jitter transfer function, corner frequency. Define the DFE with its tap values. Include the ability to de-embed the IBIS portion from the CTLE circuit data to derive the AMI CTLE portion, and generate an independent standalone IBIS-AMI model from the data. Finally, I show you how you can get a copy of my free IBIS-AMI model generator for a receiver with CTLE, CDR, and DFE for use with any channel simulator. Modeling SerDes systems in a channel simulator. Channel simulators are based on the IBIS Open Form Standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram to be simulated in a channel simulator. The block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes system include the following. The transmit IBIS-AMI model. The AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer. The IBIS portion provides a differential output to the channel. There's often a transmit package, channel, and an Rx package. These pieces can represent the differential channel. Each part is optional and may be represented using S-parameter files. There's the Rx IBIS-AMI model. The IBIS portion has differential input from the channel. The AMI portion typically contains an Rx continuous time linear equalizer, a clock and data recovery unit, and a decision feedback equalizer. Modeling a SerDes system. A key channel simulator property to keep in mind is that it considers that the entire analog content, the green area in this figure, the total channel, between the TX-AMI portion and the Rx-AMI portion is linear and time invariant. As an LTI system, the entire differential analog section of the SerDes system is accurately represented by its single-ended impulse response. This key concept enables the channel simulator to achieve its fast simulation speeds. Creating IBIS-AMI models from circuit data. IBIS-AMI model generation from behavioral data was built into the SerDesDesign.com channel simulator from the beginning. I've used this process over the past 10 plus years, providing custom IBIS-AMI models to over 40 plus companies based on the circuit data they provided me. In today's webinar, I provide instructions on generating receiver models with CTLE, CDR, and DFE from circuit data. The modeling data is typically collected from a SPICE circuit simulator. Modeling other types of transmit and receive SerDes is discussed in other SerDesDesign.com webinars. To start, let's talk about the typical SerDes system test points. This figure shows typical test points for a SerDes system. For the current discussion, test points TP0, TP4, and TP5 are used for data collection. NRZ data streams are used for modeling, though the Rx IBIS-AMI models may support PAM4 as well. TP0 is for the NRZ waveform. The data collected at TP4 is the Rx SerDes differential input. TP5 is the Rx CTLE output or Rx DFE output. The data collected includes the IBIS differential input buffer characteristics, the CTLE CDR and DFE behavioral characteristics, and output time domain waveforms. Here's the top level Rx IBIS-AMI model. There's an IBIS portion and an AMI output portion. The IBIS portion is for the circuit differential input and defines the buffer input impedance interfacing the differential SerDes channel. The AMI portion contains the algorithmic code that performs the equalization and does not have any impedance characteristics. The model discussed here is defined as nonlinear and or time variant. It can be used in the channel simulator in the time domain mode. Its characteristics is represented by its processing of its input time domain waveform to obtain its output time domain waveform. There are two basic Rx IBIS modeling options. The typical Rx IBIS buffer model is composed of an RLC circuit with additional voltage current tables per differential input pin as shown in this top figure. The IBIS buffer model is quite limiting and does not do a good job modeling the actual Rx circuit input impedance. However, per the IBIS spec 7.0 and beyond, the IBIS portion can now be modeled using 4-port S parameters. This approach is a full fidelity approach that will accurately represent the Rx circuit input impedance facing the differential channel. My experience has shown that most Rx SerDes circuit designers cannot easily separate out the S4P data for the input buffer from the rest of their Rx circuit. Fortunately, the IBIS S4P data can be obtained from S2P data. I've used this approach with my customers for many years. All that is required is to measure the Rx input differential reflection coefficient. This is called the SDD11 characteristic. To be discussed later in the slides, we'll use the SDD11 0 Hz resistance values. To convert the S2P data into S4P data that is usable as an IBIS model, set up an S parameter schematic with this S2P file as shown in this schematic below. The differential input impedance characteristics will be the same as the original S2P data when the output S4P is loaded with an infinite load resistance. Be sure to use a linear frequency sweep with the same start, stop, and step frequencies as the S2P data. We're now ready to discuss the Rx CTLE modeling options. Two types of CTLE modeling approaches are defined. One approach models the Rx circuit CTLE behaviorally with poles and zeros. The CTLE can also be defined with a list of poles or zeros or with peaking characteristics defined in the frequency domain. Another approach is to model the Rx circuit as a black box. Without a priori knowledge of the CTLE characteristics, the Rx circuit input to CTLE output time domain waveform or frequency domain spectrum characteristics can be measured with the Rx circuit input loaded into a matched 0 Hz load resistance. The CTLE discussed here uses time domain waveforms from the circuit simulations. The CTLE modeling approach as a black box. For this modeling approach, the circuit is characterized over a set of CTLE states. The Rx circuit characterization process is from the differential input to the CTLE output. It uses a PRBS waveform pattern that has a portion of the pattern with a consecutive set of M0s and N1s such that M and N are large enough to allow for state settling. The waveforms are collected with a matching 0 Hz source resistance. This approach requires de-embedding the IBIS characteristic from each of the waveforms. This de-embedding is performed automatically in the model during simulation for the specific symbol rate and samples per symbol used. After the model is generated, it can be used at any lower bit rate. Let's talk about de-embedding the IBIS characteristic to obtain the AMI model. In this figure, H of S is the Rx circuit differential input to CTLE output transfer function and is defined by the Rx CTLE time domain waveforms. H of S is the IBIS portion, H1 of S that is. H2 of S is the AMI portion that must be derived. Since H of S is equal to H1 of S times H2 of S, then H2 of S is the ratio of H of S divided by H1 of S. These transformations are carried out in the model to obtain the equivalent time domain representation of H2 of S for use in the AMI model during simulation. The CDR model is based on an industry standard bang-bang phase detector approach shown in this upper left figure. The CDR observed jitter transfer function is defined by specifying the OJTF corner frequency. The OJTF has a high pass characteristic. Jitter significantly below the corner frequency is tracked by the CDR. This lower right figure shows the OJTF characteristic of the CDR in the frequency domain with the defined corner frequency of 15 MHz. The DFE model is based on an industry standard DFE architecture shown in this upper left figure. The DFE taps can be defined in different ways. The taps can be defined with unlimited values, with limited and quantized values. The DFE can be set up to automatically derive optimal initial tap values. The DFE can automatically and continuously adapt tap values during the simulation. The DFE taps can also have a non-UI tap delays. The DFE discussed here uses unlimited tap values and fixed UI tap delays. We're going to discuss an example using the ADS channel simulator. In this ADS schematic, the Rx IBIS-AMI model is set up using the SerDesDesign.com Rx SerDes underbar CTLE CDR DFE model. This is a behavioral model that uses Rx circuit waveform CTLE data obtained from SPICE simulations along with the CDR and DFE models. The model will be used to generate an independent IBIS-AMI model. In this example, the SerDes channel is defined with S parameters. This plot shows STD21 channel characteristic. It has 24 dB loss at Nyquist, which is 12.5 gigahertz. Thanks to Silicon Creations LLC for the use of their ADS copy. Removing ADS high frequency aliasing. In this example, the S parameters go out to 40 gigahertz, the blue curve in the upper left graph. The ADS channel impulse response in the frequency domain, red curve in the upper left graph, accurately tracks the S parameters to 40 gigahertz. After 40 gigahertz, the ADS channel impulse response has high frequency aliasing. SerDesDesign.com anti-aliasing, the purple curve in the lower right graph, accurately tracks the ADS response and removes the aliasing beyond the S parameter maximum frequency of 40 gigahertz. This is done with no added delay as shown in the upper right graph. Modeling the example Rx IBIS. In this example, the Rx circuit input impedance was measured as S2P data. That data shows that the Rx circuit input resistance at 0 Hz is 53.96 ohms per differential pin. That S2P data was converted to S4P data using the approach discussed earlier. Modeling the example Rx CTLE. Any number of CTLE states are supported. This example is based on defining the Rx CTLE with 32 states, each defined with time domain step response waveforms. The IBIS buffer characteristics will be de-embedded to obtain the AMI model. For modeling the CTLE, collect the Rx circuit CTLE output waveforms with a matching 0 Hz source resistance for all CTLE states using NRZ data. The waveforms shown here are for the step responses displayed in the frequency domain. Modeling the example Rx CTLE. During simulation, the Rx model converts the Rx circuit waveform data into an equivalent AMI portion by de-embedding the IBIS characteristics from the circuit data. The Rx AMI model automatically selects the CTLE state configured for optimal channel equalization. Optimal AGC is also available. The CTLE configuration is used to obtain the Rx impulse response and the impulse response for the combined TX, total channel, and Rx. The model automatically de-embeds the IBIS from the waveform data. The upper plot shows the Rx model output impulse, which includes the Rx IBIS characteristic for a specific CTLE state. The bottom right plot shows the Rx CTLE response, which is an exact match to the original reference waveform data. The Rx CTLE waveform data represents the cascade of the Rx IBIS portion and the Rx AMI CTLE portion. During channel simulation, the Rx IBIS model is automatically de-embedded from the Rx circuit CTLE waveform data to derive the Rx AMI CTLE portion. When your simulation results are as you want, you can then generate an independent standalone IBIS-AMI model by setting the parameter enable gen IBIS-AMI to 1, along with defining the name for your generated IBIS-AMI model. The eye diagram shown here shows the effects of the CTLE, CDR, and the DFE. The messages shown below are displayed in the channel simulator message panel. The IBIS-AMI model files are generated. The DLL for Windows or SO file for Linux file contains the encoded waveform data. Now it's time to use the generated IBIS-AMI model. The generated model in this example is named Rx CTLE CDR DFE and has 4 generated files. The IBIS file, the AMI file, the DLL for Windows or SO for Linux, and a configuration file that contains all the model encoded data. The generated IBIS-AMI model can be used in any channel simulator. Only the parameters exported during IBIS-AMI model generation are used. The user can define the names for the exported parameters. Generate as many new IBIS-AMI models as you want for free. Summary. This webinar introduced you to the free Rx CTLE CDR DFE IBIS-AMI model generator. It is one of the tools I've used over the past 10 years, providing IBIS-AMI models to 40 plus SerDes customers. The Rx CTLE CDR DFE IBIS-AMI model generator enables you to define the CTLE with circuit waveforms, define the CDR with its observed jitter transfer function, corner frequency, define the DFE with tap values. It includes the ability to de-embed the IBIS portion from the CTLE circuit data to derive the AMI CTLE portion, and you generate an independent standalone IBIS-AMI model from the data. The free time-based license can be renewed for free. The tool and the generated IBIS-AMI model relies on the same free time-based license. The original license issued is for 1 month. The license can be renewed for free on a monthly basis as needed. A 12-month license is also available for a fee. The removal of the license restrictions for the generated IBIS-AMI model so that the IBIS-AMI model can be used as long as needed on any Windows or Linux computer is available for a fee. The Windows and Linux build project with the generated IBIS-AMI model source code, including training, is available for a fee as well. Use this build project as a starting point for your further customization to create any other IBIS-AMI models that have no licensing restrictions. Further considerations. SerDesDesign.com has many other free IBIS-AMI model generation tools. See the store at this website. The Rx IBIS-AMI model generator that includes CDR, CTLE, and DFE was discussed in this webinar. There's also a TXFFE model generator, an Rx CTLE generator. There's a repeater generator that includes back channel training. It includes a TXFFE and an Rx CTLE CDR DFE as discussed in this webinar. There's also an electrical repeater model generator that includes back channel training. It includes a TXFFE generator, the Rx FFE CDR DFE, and an optical VCSEL fiber PIN TIA generator. This webinar has been on SerDesDesign.com free IBIS-AMI model generation tools. Each tool comes with a time-based license. Each tool is free for 1 month. Renew the free tool license as many times as you like. See ordering instructions for the available free tools at this website. See the link below this webinar presentation as well. Well, this completes the presentation content of this webinar. I'll end the recording of the webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@SerDesDesign.com. Thank you, and goodbye for now.